Welcome to this lecture with continuing with examples in probability. We are going to deal with independence and dependence today. In particular, in the first video, I'm going to focus on IID repetitions of a particular experiment. Okay, so what happens when you have an IID sequence? So this word IID is very, very important. It will show up again and again in probability in various contexts. So IID means independent and identically distributed. Okay, so this is where this IID comes in. So let's start with a very simple example. Let's say I have X being Bernoulli. X is Bernoulli with P. So what is the meaning of this? When I say X is Bernoulli P, the random variable X takes two values, 0 and 1. The value 0 with probability 1 minus P and the value 1 with probability P. Okay, so that's the meaning of this. P and 1 minus P, right? So now, so this is like a coin toss, right? So you toss a coin once, okay? You get a Bernoulli random variable. So 1 could be the heads, 0 could be tails. Okay, so that's the way in which you can think of this as an outcome of a coin toss. Okay, so quite often you might have repeated coin tosses, right? So the first example we'll see is repeated coin toss where you'll have Bernoulli random variables coming again and again and again. So what do I have? I have a fair coin which I toss, let's say I toss n times. Okay, so I'll have n outcomes and each of these outcomes I'll denote by a random variable. So x1 is the outcome of the first toss, x2 is the outcome of the second toss, so on till xn. Okay, so each of these is the outcome of the ith toss. So xi is Bernoulli P. Okay, so so I've set P here. So P is the probability of heads when you toss the coin. So you can think of P as 1/2. Okay, so if it's a fair coin, otherwise it can be any other value. Okay, so these are the n outcomes, and we've said that these n experiments are independent in the sense that every experiment has nothing to do with the other. Okay, so if you have a situation like that, you can put together probabilities by simply multiplying. Okay, so that's the main idea. So for instance, this is your x1 to xn. So when I say xi is Bernoulli, probability that xi is 0 is 1 minus p. Probability that xi is 1. So now, if I were to ask the question, probability that x1 is 0, x2 is 0, x3 is 0, so on till everything is 0. Okay? So when you have independent and identically distributed random variables, and they ask this question, what's the probability that all of them are 0, 0, 0, 0, 0, 0? So because they are IID, because they are independent, you will have first this happening. Okay, remember once again very, very clearly, this is because of independence. Okay, so if independence is not true, if the successive coin tosses are not independent, this is always not guaranteed. Okay, so this is true only when they are independent. And on top of that, they are all identical, so they all have the same probability. So you have 1 minus p times 1 minus p, so on till 1 minus p n times, right? So this is happening n times. So this probability is 1 minus p power n. Okay, so it's an easy calculation to do when you have independent and identical repetitions of things happening. So for instance, you might ask more complicated questions. Okay, so you can ask slightly more complicated questions like we've done before. What's the probability that there is one head in n tosses? Okay, exactly one head. And it could occur in the first position, or it could occur in the second position, or it could occur in the third position, and so on. And if you look at it, there are n possible ways in which the head can occur, and probability of head is p. probability of tails is 1 minus p, and that happens n minus 1 times. So this is the binomial event, and you can see the multiplication occurring here, right? P into 1 minus p raised to the power n minus 1. There are n minus 1 tails, okay, n minus 1 zeros, and only one head. So one single 1 occurs in the sequence x1 to xn. So for that 1 you have a probability p, and for all the zeros you have a probability 1 minus p. If you multiply them together, you will get n minus 1, guys. Okay, so you have 1 minus p power n minus 1, and where does the n come from? This head p can occur either in the first position or in the second position. It has n possible places, so you have to add up all the possibilities. Okay, so in fact, if you want to write it down, this corresponds to the event 1 0 0 0 0 0 or 0 1 0 0 0 0 or 0 0 1 0, so on till 0 0 0 1. Each of these guys has probability p into 1 minus p power n minus 1. Right, so each of these guys has this probability. You add up all of them together, you will get n times p 1 minus p power n minus 1. Okay, so this is how you deal with IID events. It's easy to count these cases. Sometimes the calculation can get a bit painful. So for instance, if you want to ask the question, probability of 2 heads in n tosses. Okay, so here you will have a slightly more complicated answer, and choose 2 p squared 1 minus p power n minus 2. So you will see p squared into 1 minus p power n minus 2 is easy to see, but then how many possibilities are there with exactly 2 heads? That is n choose 2. Okay, so this is how independent events are dealt with. Okay, we can have slightly more complicated situations, which we'll look at next in the second example. Okay, so I'm going to say x is a random variable. It takes let's say 3 values, 0 1 2, and the probabilities are p0 p1 p2, and remember p0 plus p1 plus p2 has to be equal to 1, right? So this has to be a valid probability distribution. So I'm looking at a random variable which, instead of taking 2 values 0 and 1, now takes 3 values 0 1 and 2. Okay, so now I'm going to look at n IID repetitions of x, and I will call them x1, x2, x3, so on till xn. Okay, so what does that mean? Each xi takes 3 possible values, 0 1 2, value 0 with probability p0, value 1 with probability p1, value 2 with probability p2. Okay, so now so remember again, these are all IID repetitions of this random variable. So each random variable here takes 3 values, and that can happen n times. Okay, so now again you can ask such questions. So what is the probability that you have all zeros? Okay, so all of them are zeros. Once again, you can multiply all of these guys together, you will get this very simple answer, p0 power n. Okay, so if you want to ask slightly more complicated questions, so supposing you say probability of let's say 1 0, okay, so let me write it down clearly, 1 0, 2 1s, and n minus 3 2s, right? So what is the meaning of this? So I have in my sequence x1 through xn, exactly one of these values is 0. It could be anywhere, exactly one of these values is 0. 2 of the values are 1. Okay, so 1 0, 2 1s, and then all the remaining are 2s. Okay, so that's the kind of event I'm considering. So for instance, it might be 0 1 1 2 2 2 2 2, or it can also be 2 2 1 0 1 2 2 2 2, like this. Okay, like this you'll have so many events, like a lot of possibilities here. No, okay, where does the 0 come, where does the 1 come, where does the 2 come? All sorts of possibilities are there. Okay, so it turns out, if you do the calculation carefully, the one term which is easy to write down is the product of the probability. So you will have p0 p1 squared p2 power n minus 3, right? This is easy to write because there's 1 0, 2 1s, and then n minus 3 2s. How many such sequences are there? Okay, so if you count it out carefully, you will get n factorial by 1 factorial times 2 factorial times n minus 3 factorial. Okay, so this is the generalization of the binomial formula. It's the multinomial term that you get. So how many possibilities are there with so many 1s, so many 2s, so many zeros, so many ones, and so many threes. Okay, so that's 1 factorial, 2 factorial, and n minus 3 factorial. Okay, so this is the answer. So if you want me to generalize and write it out very carefully, it's if you have probability of n0 zeros, n1 ones, and then n2 twos. Remember, n0 plus n1 plus n2 will be actually equal to n. Okay, there are n of them. n0 of them are zeros, n1 of them are ones, n2 of them are twos. So if you do this, the general formula will be n factorial, n0 factorial, n1 factorial, n2 factorial, p0 power n0, p1 power n1, p2 power n2. Okay, so this is a generalization of the binomial formula. So we had before, when you have n tosses and you ask what is the probability of k ones, you write n factorial by k factorial into n minus k factorial times p power k, 1 minus p power n minus k. This is a generalization of that fact. Remember, n2 is n minus n0 minus n1, and similarly p2 is also 1 minus p0 minus p1, right? So remember that. And n2 is n minus n0 minus n1. So this is a fact that needs to be satisfied. Okay, so you can use this formula to add up probabilities, and when you have IID repetitions, excuse me, you can use this formula to add up probabilities when you have IID repetitions. Now you can also generalize this. I'm not going to talk about it here, but it's possible. Okay, so now there's this slightly different example I want to talk about. Suppose you toss a coin 20 times. Okay, so I'm going to toss a coin 20 times, and I will define n1 as the number of heads. Okay, remember this is also going to be IID. We'll make that assumption in first 10 tosses. And I'll say n2 is the number of heads in the next 10 tosses. Okay, so what do I mean by this? When I say first 10 tosses, toss 1 to toss 10. When I say next 10 tosses, I mean toss 11 to toss 20. Okay, so this is the thing I'm defining. I'm tossing the coin 20 times. The first 10 tosses, how many heads I got. The next 10 tosses, how many heads I got. So that's the two random variables, n1 and n2. Okay, so n1 itself is easy to write down, and n1 is going to be binomial with these two parameters, n comma p. So p is going to be the probability of heads of a single toss. Okay, so similarly n2 will also be I'm sorry, here, so this 10. Okay, n2 will also be binomial with 10 and p, right? So what do I mean by that? So probability that n1 is k, so k equals 0 to 10 is actually 10 choose k, p power k, 1 minus p power n minus k. The same thing holds here. Probability that n2 equals k, it's again the same thing. 10 choose k, p power k, 1 minus p power n minus k. But remember, n1 is a function of what happened in the first 10 tosses, and n2 is the function of what happened in the next 10 tosses. And these two are not connected in any way, because they're all from independent tosses, right? So as a result, what happens is n1 is independent of n2. Okay, so that's the important result here, which we will use. So the important observation is that n1 and n2 are independent. Okay, because they did not overlap in any way, right? So n1 is a function of what happened in the first 10 tosses, n2 is a function of what happened in the next 10 tosses. So these two also will be independent. Okay, so when you have derived some functions with independent random events, you will also have random variables being independent. Okay, so n1 and n2 are independent. So if somebody were to ask you a question, what is the probability that n1 is 0 and n2 is 10? Okay, one can multiply. Okay, because they are independent, this implies one can multiply these things. So you can do probability of n1 equals 0 times probability of n2 equals 10. Okay, so if they are not independent, you can't do this multiplication. Okay, so because they are independent, one can do this multiplication. So this is easy to do. So probability that n1 is 0 is 1 minus p power 10. Probability that n2 is 10 is p power 10, and you get a very nice answer of this form. Okay, so if they were dependent, then you have to do more complicated calculations, but for independent IID guys, since they were functions of independent events, this works out very easily. Okay, so let me do one more example of how this IID repetition comes in and how it's useful. So we've been talking about this balls into bins experiment a lot. Okay, so let's say we consider n balls thrown independently and uniformly at random into m bins, right? So this is the experiment we've been considering a lot. And remember, each ball, what you do with each ball is uniform. The ball can go into any bin, and it's also independent of what you did with the previous ball or the next ball or anything like that. Okay, so there's no connection between these things. So that's very important. So one can think of this as an IID repetition. Okay, so let's say I define xi to take m values 1 to m, and I will say it's uniformly distributed. Okay, so what is this xi? This is the bin into which the ith ball landed. Okay, so so now I have a sequence of random variables x1, x2, xn. Okay, with xi denoting the bin into which the ith ball landed. Okay, so this is an IID repetition. Each xi is uniform and takes m values 1 to m, each with probability 1 by m, and I have an IID repetition. So this balls into bins is like an IID repetition in this sense. Okay, so in this sense, if you were looking at the number of the bin in which the ball landed, and at the end of the day that's of interest to you, that's your outcome, you can think of it as an IID repetition. So you can use this to simplify some of the calculations in balls into bins. It's not always very easy, but you can use this to simplify some of the calculations. It will help you. Okay, so this is way in which IID repetitions can happen in simple experiments. Coin toss was one example. Even balls into bins falls under that category of examples of IID repetition in some sense. Okay, so the last example I want to do is quite important, and it will enforce the idea of independence and dependence and all of that. Okay, so I'm going to consider the case where x and y are binary random variables with a joint distribution pxy. Okay, so there is some joint distribution for x and y. They are binary random variables. What do we mean by binary? X takes two values 0, 1. Y takes two values 0, 1. Okay, so I'm going to say I know the marginals of these two random variables. What do I mean by marginals? I know px of 0 and px of 1, let's say, is uniform. I know this is half. And likewise, I know py of 0 and py of 1 are both half. Okay, so marginals are known. Marginals are uniform, right? What can you say about the joint distribution? Okay, that's the question. So the marginals of these two random variables, they are jointly distributed, I know that, and then I have their marginal distribution. I know that x itself is uniform, y itself is uniform by itself. What can we say about the joint distribution pxy? Now, a lot of people would immediately say x and y is independent, so pxy is actually going to be 1/4. So what do I mean by pxy? There are 4 values, right? So you have so it's convenient to write it like this in the form of a table. So you have your x, y here, x is 0, 1, 0, 1, and this table captures pxy. Right? So for instance, this would be pxy of 0, 0. This is pxy of 0, 1. No, I should be careful here. I'll put x here and y here. Okay. So pxy of 1 comma 0 and pxy of 1 comma 1. Okay, so a table like this captures the joint PMF. So I've said the marginals is half. So a lot of people would simply multiply half with half and put 1 by 4 here, 1 by 4 here, 1 by 4 here, 1 by 4 here. Okay, so that is just one possible joint PMF which gives you these marginals. Okay, there can be many other joint PMF. So for instance, you can write something like this, right? So I could have something like 0.1 here, 0.4 here, 0.4 here, 0.1 here. Okay, so this you can check is a valid joint PMF. You add up all of them, you get 1, and your marginals are still 0.5, 0.5, 0.5, 0.5. Okay, so how do you get the marginal of y? You have to add these two things, 0.1 plus 0.4, that's 0.5. Okay, for marginal for y equals 1 is 0.4 plus 0.1, again 0.5. So every marginal is 0.5. So x and y are still uniform, but the joint distribution is not the independent case, right? So if it's the independent case, I should get 1 by 4 here, 1 by 4 here, 1 by 4 here, 1 by 4 here, but this is not that. This is some other joint PMF for which you have x and y being uniform. So this is a dependent situation. So x and y are dependent. Okay, so you can check why that is so, because probability that x equals 0 comma y equals 0, all right, is equal to 0.1, and it's not equal to probability of x equal to 0 times probability of y equals 0. So this is not true. So because of that reason, you have this being dependent. You can see why that's true, no? Because this is 1 by 2 into 1 by 2. This is 0.25. On the other hand, this is just 0.1. So this is a joint distribution which is dependent. So in fact, this is not the only joint distribution for which this is true. You can have any other joint distribution. So you could take, for instance, another joint distribution, xy being 0, 1, 0, 1. I can take this value to be some a, and I'll put half minus a here, and put half minus a here, and a here. And a could be any value in the range 0 to, I could take it from 0 to half. Okay, so for any a from 0 to half, this joint PMF will always give you marginals which are uniform. Okay, for both x and y. So how many joint distributions are there which give you marginal uniform PMF for for binary valued random variables? Actually an infinite number. Okay, it can be any number. Okay, you take any a from 0 to half, you will get it. In fact, there's an extreme example I can give you where it will still be marginal in that fashion. For instance, you could take a equals 0. If you take a equals 0, you have 0, 0, half, half. Okay, so it's very sort of an extreme. So x and y together take only two values. If x is 0, y is 1. If x is 1, y is 0. That's all. Okay, so it's kind of deterministic relationship between x and y. Or you could take a equals half. Okay, in which case x and y are equal. Okay, x is 0, y is 0. X is 1, y is 1. But still, the marginal distribution is uniform. But the joint distribution is anything but independent. What is the only independent case? If a is equal to 1 by 4, you have independence. Okay, so remember that. A equals 1 by 4, you have independence for x and y. Okay, so for a not equal to 1 by 4, x and y are dependent. So this is something, an important lesson to just to reinforce the notion of independence and where it comes from. Just from the marginals, you can't guess anything about the dependence or independence. You need the joint distribution, and there can be any number of joint distributions which give you the same marginals, and the independence case is just one possibility. Okay, so hopefully you got an idea of how to use independence, what is the meaning of IID repetition, and all of that in this lecture. Thank you.